In previous videos, we have learned how to build molecular orbital diagrams of simple molecules, and we have seen diatomic, also diatomic but heteroatomic, and also small polyatomic molecules. And the take-home message of all this is when the atomic orbitals, and say that this is the atomic orbitals of oxygen with their 2s2, 2p4, and the other oxygen is 2s2, 2p4, and they combine, they give a specific molecular orbital diagrams that is the result of interaction of those waves of probability that the atomic orbitals are. So you have to fill up 6 electrons come from one oxygen, 6 from the other. So you need to put 12 electrons. I should put the arrows, but I'm just going to put it here to make sure that this follows Hund's rule. This explains why dioxygen is paramagnetic, etc. Notice that this same approach can be applied to other molecules, and some molecules start being very complicated, so we will have to simplify some of the theories to understand the molecular orbital diagrams of more complex molecules. And speaking of complex, this is the molecular orbital diagram for this coordination complex, the hexa-aqua iron 2. And this is an octahedral because it has 6 ligands, and iron 2, so iron neutral would be a D8, but this is a D6, so the configuration of iron 2 is D6, so the electrons, it's 6 electrons coming from the iron, and we have 6 waters, each of water as a ligand. Remember, it's a monodentate ligand, so each water provides 2 electrons. We have 6 ligands, you have 12 electrons. So I need to place 18 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, oops. Let me sure. 1, this is 8, this is 12, right? Yeah. 14, 16, 18. Now, notice that this is my highest occupied molecular orbital, also known as LUMO, the LUMO is the lowest unoccupied molecular orbital. What we are going to do from now on when studying coordination complexes is zooming out into the area that really interests us, because this explains the difference between these, explains color, explains magnetism, and in general it explains the chemistry. All the chemistry, or most of the chemistry of compounds, can be reduced to the characteristics and the energy between the HOMO and the LUMO. So let's focus now on color. What we mean by explaining color when we talk about the difference between the HOMO and the LUMO. Well, an example is when you have these two coordination compounds. Notice that we just substituted one ammonia here by one chloride. They are all chromium 3, but this one is orange and this one is purple. Now, we must say that most of the times the difference between the HOMO and the LUMO is so large that it falls in the UV region. That is, we cannot see the light that interacts with the electrons in the HOMO and the LUMO. However, in coordination compounds, the difference, and let me show you here, if this is my HOMO and this is my LUMO, the difference in energy between the HOMO and LUMO is small enough, and this is typically an exception, that this is why it explains why coordination compounds are so colorful. So what do we mean by a coordination compound being colorful? Well, if you emit, this would be white light, some of this white light will be absorbed by the coordination compound, such as this one, and the rest will be transmitted. The rest will not be absorbed. So this means that if I'm here, this an eye, okay, let's put a nose, visual cap, okay. I'm just very excited to see here that this compound has this color, even though this color is actually the color that has not been absorbed. So this is the theory of color that we will have to learn. In general, when you look at an object, the color that is absorbed is the color that has not been absorbed. So sorry for one is A, the other one is O. In other words, if you emit light on and white light, all ranges of of wavelength on an object, the color that is reflected, then the color that is observed, is the one that is not absorbed. So, and how do we know the relationship between the color that is absorbed and the color that you see? Well, and this is why you have this color wheel. The color wheel gives you the relationship between complementary colors. And you have here these numbers. These numbers exemplify the wavelength, and as you remember, the lower wavelength implies it has a lot of energy. This would be violet, and lower wavelength would be close to the ultraviolet, and on this extreme it would be a higher wavelength, a lower energy, or if you will, closer to the infrared. It's not a coincidence that it's called infrared because it's below the red, or ultraviolet because it's beyond the violet. Okay, so the color that is absorbed is related to the difference between the HOMO and the LUMO. So for example, if this is my highest occupied molecular orbital and this is my lowest occupied molecular orbital, and here's an electron and here comes a photon of light, if the molecule absorbs this photon of light, it means that this photon has the energy, the exact energy that matches the difference between the HOMO and the LUMO. So a question would be, a pigment is blue and another one is yellow. Which one has the smallest energy between the HOMO and the LUMO? Well, let's look at the color wheel. For the blue, if a pigment is blue, that's what's observed. The absorbed is, so if it's blue, it means that it absorbs in the orange. That is in the range of 620, 580 nanometers. The one that is yellow means that it absorbs the violet, and the violet has a range of 400, 430. Definitely the yellow, because it absorbs a photon of smaller wavelength, of larger energy, will have a larger gap. In this case, the yellow compound will have the largest energy difference between the HOMO and the LUMO. We will practice more, but we have to make sure that we understand these basics before we jump into transition metal compounds.